Okay, thank you very much for look at this video of the uh, AI and data science for civil engineering. So this time we are going to give you some knowledge about probability first. So the probability have been already been told in a lot of lectures, I think. But here for AI data science, we need to some review some fundamental basic concept and knowledge about probability and statistic. And today's contents is including the probability theory basic and binomial distribution. So firstly, let's take a look. What is uncertainty? So uncertainty have been categorized to two type of uncertainty. Aleatory uncertainty is means that something uh, that is happens we cannot predict and is have a inertial uh, unpredictable things like earthquake or rainfall. They didn't have a certain pattern or certain reason. They may have some certain reason, but we cannot know, we cannot predict them. The other uncertainty is come from the epistemistic uncertainty. That is because or the tool or knowledge are caused some noise uncertainty, something like sampling methods that we use in some sensors have some noise, or we have some human mistakes. And we have the some measure to some method to measure the uncertainty, like mm, sample. And for example, is the meaning the meaning of sample is like to do for some uncertainty event, right? Some answer issue we want take a measure. For example, flip we want to know the flip a coin. We want to know the probability of head or tail, so that flip a coin to see the side of the head or of the tail is a sample. Sample space is uh, for example, a flip a coin case is a two-sided coin, right? So there'll be two uh, probable result, head or tail, right? So uh, sample space is just two sides of coin, right? So there's no third surface of the coin, third side of the coin. And events it means that it's like when I flip a coin and I find the side is head. This events. So there be can be multiple events like I flip two flip coin twice, and the first time is head, second time is also head, or first time is head, second time is uh, tail. Right? Those events can be many, right? It depending on what's happening there. The sample space just two possible choice. Uh, and probability variable is a target that we are studying. For example, a flip coin, the chances of uh, hide head side up, right? And we can take a look at the event and sample space. So right now, for example, the whole bracket is the whole square is a sample space, whole sample space. So E is some certain event, and E bar is a complementary event. Some event exclude E. So S is sample space. Phi is impossible event, which is zero. So this is some basic fundamental examples. So classical probability P bracket E, it means that P is the probability of the event, right? Event A, right? So PA is given by the number of elementary events for A, the number of all events, right? Uh, so for example, the toss a coin, toss a coin, one side, right? One coin. So the uh, probability will be the events of the sample space, right? For the sample space, there are two events, head or tails, right? So there's only two possible events. So 0 0.5, 0 0.5. So if I toss coin twice, right, then the sample space and possible event will be head, tail, 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 head, tail, head, right? So it'll be each of them will be 25%, 25%. Uh, so let's do an exercise. So uh, simulating one coin toss game for human for huge amount of trials, right? A lot of trials, many trials. So so let's simulate. Firstly, we should simulate one coin toss and record head or tails in each trail, right? So I need you to write a Python program, to do so. After I learned Python all of this way, there's some tips that using library of random important and use library at random. So you need import random and make R equals random random. So that will be a random number from 0 to 1. This will give a random number from 0 to 1 randomly, right? So so because the random chance is 50% if it is smaller than 0 0.5, right? 50% if it was larger than 0.5%. So I can define it. If it is smaller than 0 0.5, it is something something. If it is larger than 0 0.5, it will be something something, right? So please do the exercise and write it. Please stop the video right now and start a new Google Collaboratory notebook file. And in the cell and try to run a program to simulate one coin toss and uh, record each tail and head and tails in each trail, right? Please try to write this kind of program and stop it right now. Okay, I guess you already tried to write this program. So let's see what is we can uh, what kind of program we can write for this exercise. Because this is a video, so I cannot ask you, some of you, to come up to write the program, but I believe you already tried. And so firstly, we import random, and we define coin here. Define coin. P equals 0 0.5 means this is a default import input argument with some default value of 0 0.5, right? So this P means that the probability of head side up, right? And so R equals random random. So if R smaller than 0 0.5, the coin equals head. else coin equals tails, right? And return coin. So heads and tails is a string, right? And then you print coin, right? Then you call the coin, then it will tell you is head or a tail if you put a probability inside here. Now, let's simulate M coin toss game for many trails, right? So right now you have a one coin toss simulator, and then you can do it for M times, right? M times. So then you can record each result and into a list of string, right? From this string, you can observe how many times head is up of all the trails, right? Now you can uh, pause the video and do the exercise. Okay, I think you already did the exercise very well. So let's see what is going on here. So it's a very simple question, function. So the name is coin trail. M equals 10. 10 is the default value of M times, right? So has records number of has is recorded. So for uh, I in range of M, I run the function of coin, which is P is probability 0.5. So if coin equals has, so I use this line. In this line, it is run the function of coin and return the result, head or tail, right? So I only run when the coin result is equals to head, and then makes has plus equals 1. So here plus equals 1 means that has equals has plus 1. So in Python, it can be writing on has plus equals 1. And then I return the number of has divided by m, which is the ratio of the has up after m times trying. So you can think, okay, so I have 100 times of coin trail, so they can returns of 0.5%, 0.5, right, of the ratio. So in the beginning, because it's head is 0, so only the times that it comes head, it will be counted to the heads. Okay, so I can do the simulation of m time of choice. Okay, and uh, so for each trail, it will do 100 times of trails, right? I will do 10 times of the result and see how difference, right? So for each times, for one trial, it'll do 100, 100, it toss 100 coins, right? Right. And uh, coin trail, right? Because m equals 100. And then I do it one by one, so it will returns the result that we append to a list of trails, right? It give you a series, a number that tell us that how many trails I did. I use simulate 10 to automatically give n because it's first variable of 10. Okay? So please run the program and see what is the result. And please print out. So it returns the uh, sum of all the results. So please print this simulate 10 times and see what's output of the result. Sample space, okay? But let's see this example. This example is come from the book of Professor An. It's a very famous book of probability concepts in engineering. It's a very famous book. So please uh, uh, look this book for more details of the basic concepts of of uh, uh, probability. And I use this example to see what is probability use for civil engineering, right? So consider again a simply supported beam A, B as shown in this figure. Okay, here is a supported, simply supported, okay, in AB. So if a concentrated load 100 kilogram can be placed on any of the 1 meter, 1 meter interval points. So there will be 10 interval points here, right? Each of them is 10 interval points, right? So it will be 10 meters long. So there'll be uh, here, or 1, 2, 3, and 2, 10, right? So the sample space of RA will be as follows, right? 0 means that this one acting on here, right? 10 means this is acting on here. So 100 means that acting on here, right? So the reaction force will be different. The sample space of RA and RB are all pairs of RA and RB, such as uh, RA plus B equals 100 belongs to the sample space. Roughly, this small space is in figure, this figure, right? So you can see, so reaction force as A, reaction force as B. So here is a sample point. If we plot them out, which each case, right? You can see that not all of the combination are possible, but we need to enter the condition for the two of them that their sum will be 100 kilogram based on the physical rule. And so for C, if 100 kilogram load can be placed anywhere along the length of the beam, the sample space of RA can be represented by a straight line, right? between the sample space of RA, 0 to 100, straight line, right? Continued result. There's the corresponding space of RA and RB. So there are two variables, right? RA and RB will be this line, right? Be this line. And in figure 2.5, an event may be defined as uh, larger than 20 and 40. So it's between this one, right? Whereas figure 2.5D, an event of RA and B may be between 20 and 80 to 40 and 60. So this is the range of the space. Next, consider the load can be 100 kilogram, 200 kilogram, 300 kilogram, and can be placed anywhere along the beam. In this case, the sample space of RA and B contains all values between 0 and 300 kilogram, as represented in the space of this. So the sample space of RA or RB will be 0 to 300 kilograms, right? And then the sample space of 100, 200, 300 kilogram of RA and B will be something like this. So depending on the definition of the uh, issue problem, the sample space can be changed, and you can measure the length of the sample space to get the probability of RA or RB. So here is or concept. Here's concept or concept of the probability variable. Continuous variables is like x equals to a to b. This is some range. Weights, for example, the weights of cars, x equals 1 to 10 ton. And life load on structure X, so structure is X equals 100 to 300, continued. Any number will be fine. Reinforce X equals to 10 to 300 millimeter, or sometimes it can be a discrete variable. So X is some defined finite numbered value, x1, x2, x3, and xn until xn. For example, number of cars, 0, 1, 2, 3, right? Coin size, head or tail, the dice is between 1 to 6, right? Some uh, decided number of the result, okay? And let's see the probability distribution. For the continued variable, the value is continued. So there will be a probability density function or PDF, something like this. This shows the density of the probability, density probability. So in unit uh, variable, unit length of the string, space of the variable, what is the probability in unit of the variable? And if you accumulate them, then you can get a cumulative distribution function. So this means that, for example, here will be the probability that x is smaller than this value, right? Smaller than this value. So it's accumulated from 0 to this value. So it's uh, exceed probability, right? And discrete variable, and for the case of discrete variable, so it will be the probability mass function, like here. So for each value, they have a mass, a probability of what is a portion of the uh, to be as this value. And there's also cumulative distribution function, but it's not a smooth curve, but like a stairs uh, curve. It's a cumulative distribution function. So for continued one, we use PDF. For the discrete one, with the PMF. And let's see the some basic rule of probability. And for probability, it should be larger than zero, as or equal to zero. And for the probability, but is also smaller than one. And so the sample space, if I use the probability of sample space, is equals to one because including everything. And the probability of A1 united or union with A2, it should be probability A1 plus probability A2 if the A1 A2 are independent event. So P means the probability, and A is the event, S is the sample space. Okay. So conditional probability is also very important for the next part of our Bayesian theory. Is the defined by this expression. So it means that the probability of event A1 under the condition of A2. So we know A2 is already definitely going to happen. So the sample space, not in the sample space, right? So anything that happens outside of A2 is impossible right now. So in this condition, A2, what is the probability that A1? Obviously, this probability will be larger than without the condition, which is a sample space, right? So the probability of, so if A2 happened, what is the probability of A1 happens, right? So right now we know right now A2 happens, so it will becomes normalized probability of A1 by the probability of A2, right? So you can consider that the area of A2 divided by the area of A1 divided by area A2 instead of the probability A1 is the ratio of A1 divided by S, the sample space. Thus, we can know the PA1, probability A1 and all the condition is the conditional probability of A1 and A2, multiple the probability of A2. So what is the total probability is that of uh, defined by this equation. So we have some event of A, and also we can split the space, sample space to some subspace or some event, E1, E2, E3, right, or others. So once we split them, uh, we can using this equation of A can be happen in any of them. So this equation is means the uh, probability of E1 and the condition event of E1 to A, right? This means that the probability if under the condition of E1 multiple the original condition of U1, okay? Also plus that the part that happens to A, E2, and also that E3, right? So it's listened very complicated, right? So let's take a example. Let's take an example. Uh, okay, so here is a sample space. So sample space can be split to multiple event, E2, E1, E2, E3. All of them are combined together is sample space, right? So A is an event. So A the event can be happens of in this area, okay, in this area. So I just so this area is this part of probability is this one, right? The under the E1's probability of A and multiple the portion of E1, right? And then I sum to this part, I sum them together, will be the total probability of A. So why we need to this kind of equation, right? Well, let's take a look of this example. The flooding of a river in the spring season will depend on the accumulation of snow in the mountains during the past winter season. Okay, the accumulation of snow may be described as heavy, normal, and light. Okay, three events, right? Three event. So clearly, if the snow accumulation in the mountain is heavy, the probability of flooding in the following spring will be high. Whereas if the snow accumulation is light, the probability will be low. So it's conditional uh, probability, right? Flooding, of course, may also be caused by rainfalls in the spring uh, with following notations. So F equals to it means the occurrence of flooding in the river. And H is heavy accumulation of snow. N is normal accumulation of snow. Light is R is light or including no accumulation of snow. So also see the probability of heavy accumulation of snow of occurrence of flooding in the river will be 90%. So if it's a normal accumulation of snow, the probability of flooding is 40%. And if light is 10%, because also it's not exactly no flood probability, but it's also because it's also depending on the rainfall falling, right? Whereas as a given winter season, for probability of heavy snow is 20%, normal snow is 50%, and light snow is 30%. So total probability of flooding in the river during the following spring season will be uh, calculated by the total probability of uh, heavy snows conditions flooding probability, the probability of heavy accumulation of snow, right? So these two multiple together. And the probability if there's a normal snow, accumulation of snow, right? And its probability of flooding. And if the the accumulation of snow is light, the probability of flooding next spring is here, and the probability of light accumulation of snow multiplied together. So you give a portion or weight of the conditional flooding probability to them, and then you get a overall weighted probability of snowing. So we know that it will between 90% and 10% and 40%. Any uh, so we know the distribution of probability of them. So we just weigh them and sum together. So it's very easy. So we can get a probability of flooding in the spring in total case. So we can do some survey to for each case what is going to happen, calculate the probability, and to do some useful method for design, right? For example, every year, many earthquake happens around Japan, and in seismic design, earthquakes was separated to a few level by their intensity, right? Large level earthquake have a small occurrent probability, and larger earthquake may cause structural damage in higher probability. Uh, Calculate the total damage probability, PD, right? So damage probability can be give three case class: small earthquake, middle earthquake, large earthquake. We didn't know that there will be 100% of earthquake that we don't damage, right? Because the building and bridges, their quality and their construction year uh, may be different. It's difficult to say it's 100% damage or not damage, I think, right? What you can predict, okay, there's a 10%, 30%, 50% probability of damage of earthquake in the three cases. Okay, also, the probability or current probability of the earthquake, if of each class, is like 0.002, 0.05, or 0.2 for small and medium and large uh, probability. So you can use this to calculate the total probability of seismic damage using these equations. So functional evaluation earthquake, or FEE, is a seismic hazard design spectrum that has a relatively small magnitude, but may occur several times during the lifetime of bridge. So FEE is taken as a spectrum based on 20% probability of exceedance in 50 years. And safety evaluation earthquake is some earthquake is larger than FEE, but uh, smaller probability of occurring during the lifetime of the bridge. Let's say in 50 years, it will have 5% probability, right? And so in the design earthquake, uh, the design spectrum is practically evaluate that based on 70% probability of exceedance 75 years of a bridge. And so we give using Python program, using the total probability, using the Python program, we can do some calculation of the damage probability uh, for the bridge, right? And for example, the fragility, which is means uh, bridges damage probability due to different type of earthquake, stress of earthquake, like small, medium, and large, which is 0.1%, 0.1, 10%, 30%, and 50%. And hazard means the recurrent or occurring probability in 50 years. So it's 25% and 0.02%. Sorry, I think this should be 0.02%. Yeah, so it's more zero here. And probability of damage will be NumPy sum frigidity multiple hazard. So what this means, this multiple marks. So this is an NP array and this is another NP array. So this multiple will do element wise multiplication. So this one multiple this one, this multiple this one, this multiple this one, and you sum them together is becoming this equation. So here, the frigidity is a conditional probability of structure will damage under some certain earthquake level, right? And hazard is the probability of earthquake happens in totally 50 years, right? So we can see print output that or structure safety seismic damage probability is uh, something like this, and the reliability is 1 minus PD. So we calculate the structure damage probability is 5%, reliability is 95%. So it means that in 95%, the structure is safety, in 50%, but there are also 5% probability that structure may experience damage. Oh, okay. So let's please consider this question. So structure damage level is D1, D2, D3, and the cost of damage level is C1, C2, C3. So if light structure damage, the cost is very light, right? Maybe some glass, maybe some contents of the bookshelves falling down, so we just need to pay for cleaning and rearrange all the things, or we just install the glass what we find. If the some shutter have cracks, then we should fill the cracks. If shutter damages more, then we should do some retrofit work or repairing work. Will cost more structure. So the cost of the structures is different in different damage level. So the probability of damages is P1, D1, PD2, PD3 due to the probability calculation that we did before, right? Of course, uh, this probability is very light probability damage. So that's why it's very large probability damage, right? So that is reliability is very high. But for small damage, the probability damage probability is higher, right? For large damage, the probability of damage is smaller because structure is designed very strong. So the risk of each level will becomes a probability of D1 multiple cos 1, probability of D2 of cos 2, and probability of D3 of cos 3. So the risk of some event is means the probability multiple the consequence. So in the most of the case, a consequence is the cost and in the unit of money, measured by money. So we can see the total risk of earthquake damage in the 50 years of serviceability time will be using this equation. P probability of D1 multiple cos 1 per D2 multiple cos 2 per D3 multiple cos 3. So this is a risk evaluation of the building. So please try in Python to do some kind of risk-based design for building, bridge, dam, port by some risk analysis. So please consider this question and please do some practice in programming to do so. Hope it can help in your study of concept of designing of other structures. Thank you very much.